The next sorting algorithm that we will be implementing that we have on our curriculum is quick sorting algorithm. So quick sorting algorithm is also one of the divide and conquer based algorithm only. That basically means that whatever the entire array that we get, we will divide it into two parts and we will basically apply the same logic on both the parts that we get in the array. And if you remember the merge sorting algorithm that we have implemented, right, we are dividing the array into two parts based on the middle index that we are calculating. Basically, whatever the length of the array that we are getting, we are dividing it by two, and basically applying the same merge sorting algorithm on the left part of the array and on the right part of the array based on the middle that we are getting. Here also the entire logic will remain same, but the way we are going to divide the array into two parts is what makes the difference in the quick sorting implementation. So the entire logic of quick sorting basically depends upon a specific index calculation. That index is nothing but pivot index. So as part of the pivot index calculation, what exactly we will do is we will try to pick a particular element in the array and we will basically try to move that element into its perfect position. That means that when we sort the array, whatever the position that we get that specific element, right, we will move that value to that particular position. Okay, so that whatever the index that we move that element into, that index is nothing but pivot index. Okay, and one more thing that you have to remember about this pivot logic is that whatever the index that we move that particular element, right, all the left values will be smaller than whatever the value that we have picked, and all the right side values will be greater than that specific value. What do I mean by that is, for example, let's just assume that we have got an array of values, what you see on the screen. Basically, we totally have 7 values which are available at these indexes that I'm putting on the screen. So totally we have 7 elements in the array that we have got. Now our ultimate aim is to pick a element. As part of the pivot logic, we will pick a element and we will move that value to its perfect position. So what do I mean by that is, for example, so if I sort the values that I have got in the array, right, the resulting array that I basically get is -10, -5 and -2, 1, 3, 4 and 7. So as part of the pivoting logic, what we will do is we will pick a value and we will move that value to its perfect position. For example, if I pick the value -10 as part of the pivoting logic, right, I need to move this value to index 0, because once I move that value to index 0, that itself is a perfect position, right? Because after sorting the array, -10 is available at index 0. Similarly, if at all if I pick the value -2, I need to move this -2 to index 2, because in the sorted array, the index of -2 value is index 2, and that is the ultimate aim. Along with that, as part of the pivoting logic, we will make sure that while moving that value to its perfect position, all the left side values will be smaller than that value and all the right side values will be greater than that specific value. Okay, and one of the important thing that you have to remember in terms of pivot logic is that pivot logic basically does not mention that which element you need to pick for moving that specific value to its perfect position. You can pick any value by making sure that we need to move that value to its perfect position, making sure that all the left values are smaller and all the right values are greater. So those are the only two conditions that we have to follow when we implement the pivot index. But whenever I implement, right, basically I'm thinking about implementing the quick sorting as well. As we divide the array and we call the same function recursively, right, I will basically pass the start index and end index in the specific calculation as well. And at this point of time, mentioning these details will definitely create little bit of confusion, but trust me, once you implement the quick sorting algorithm, you will understand the entire flow very clearly. Okay, so in my pivot logic, whatever I implement, right, I always pick the starting element of the part of the array that I am going to get. So in the array that I have got here, right, if I need to implement the pivot logic, I will always pick the element that is at the start. In this case, the element that is at index 0, which is nothing but 1, it itself is the value that I need to move to its perfect position, making sure that all the left values are smaller and all the right side values are greater. That basically means that I need to move 1 to index 3. Okay, I need to move 1 to index 3 and all the left side values are smaller and all the right side values should be greater. That means these side values should be greater and these side values should be smaller. So how we will implement that? Let me explain that logic now. In the beginning, I am going to assume the very first element in the array as the pivot value. So right now I'm going to assume pivot value is nothing but 1. Now once I pick this value 1, right, whatever the index that I'm currently at, it itself could be the perfect position for that value, right? So in the beginning I am also going to assume pivot index is nothing but whatever the index that I'm picking the value from, that is I'm picking the value 1, which is nothing but is at index 0. So in the beginning pivot index will also be 0. Now what we need to do, this pivot value 1 we need to compare with the remaining values we have in the array. We need to move this value 1 to its perfect position, making sure that all the left side values are smaller and all the right side values are greater. For that we will basically go to each and every element and we will try to compare it. So now I will start my comparison from index 1. The value that we have at index 1 is 4 and 1 and 4 basically gets compared. Obviously 4 is greater than 1, right? And it is obviously coming after 1. According to our implementation, all the values on the right should be greater. So 4 is in its perfect position. So we don't do any sort of swapping. Immediately we will move on to the next element. The next element that we have is minus 5. Right now 1 and minus 5 will basically get compared. Obviously minus 5 is smaller than 1, right? So it should basically come on the left side. That's the reason why what we will do is, in the beginning pivot index we assumed it as 0, right? We will basically increment it. So it will become 1. Once we increment it, we will basically swap these two values. Okay, that basically means whatever the index value that we are comparing with the value that we have at pivot index. Once we swap these values, right, the resulting array will be 1, minus 5, 4, 3, 7, minus 2, minus 10. Okay, so far we have compared these two values. These remaining 4 values needs to be compared. As a result, we will move on to the next element, and the next element is nothing but 3, and 3 and pivot value, which is nothing but 1, will basically get compared. Obviously 3 is greater than 1, right? And 3 is coming after 1 itself, so we don't do any sort of swapping. And we will move on to comparing the next element. On the next element we have 7 and 1 will basically get compared. 7 is greater, so we don't do anything. Immediately we will move on to the next element. Minus 2 and 1 will basically get compared. Now minus 2 is smaller than 1. Right now the pivot index that we have is 1, so we will increment it by 1, so we will get 2. Now we will basically swap the value at index 2 with the value that we are comparing. As a result, the resulting array that we get is 1, minus 5, minus 2, 3, 7, 4, minus 10. Okay, so the only element that we are still pending for comparison is minus 10. Now minus 10 is basically gets compared with 1 once again. Obviously minus 10 is smaller than 1, right? So we need to swap it. For swapping, we will increment the pivot index by 1, so we will get index 3. The index 3 and this value will basically get swapped. Once we swap these two values, the resulting array is 1, minus 5, minus 2, minus 10, 7, 4, 3. And there are no more elements in the array to compare. Now we are basically done with the comparing all the values that we have in the array. Now if you observe the resulting array that we have got after all the comparisons, we still haven't moved 1 to its perfect position, but Just look at the swapping operation that I will do right now. After that, the the value 1 will be moved to its perfect position. Along with that, all the left side values will be smaller and all the right side values will be greater. Right now, we are done with comparing all the values, and the pivot index that we have in the end is 3. That means pivot index is pointing to -10. And in the beginning, we assumed that we will pick up the very starting value we have in the array, right? As a result, we assumed pivot index is nothing but index 0 and the pivot value is 1. Now what we will do is we will basically swap the whatever the index that we picked up the element in the beginning for pivoting logic. In the beginning we picked up the value 1 and it is available at index 0. So what we will do is whatever the pivot index that we have left in the end after done with all the comparisons, we will swap these two values. Once we swap these two values, right, the resulting array will be -5, -2, 1, 7, 4, 3. Okay, do you see now? 1 we have moved to its perfect position, because if you compare with the values that we have in the sorted array, 1 is at index 3. If you see the resulting array that we have got after swapping all the values, 1 is at index 3. Okay, and one more thing, if you observe here, is all the left side values are basically smaller than 1, and the left side values are basically -2, -5 and -10, and all the right side values that we have are 7, 4, 3. Okay, I'm mentioning this very important thing right now. I am saying that all the greater values will be on the right side and all the smaller values will be on the left side. That doesn't mean that all the values are in the sorted fashion. The only thing that is true is whatever the pivot value that we picked, that will go into its perfect position, and all the left side values will be greater. That doesn't mean that all the values will go on in the sorted fashion. All the left side values will be smaller, but that doesn't mean that all the left side values will be arranged in the sorted fashion. Okay, in the end, the pivot index whatever we have is nothing but index 3, right? Because we moved the 1 to its perfect position. 1 is available at index 3. Okay, so this index is nothing but pivot index. As part of this pivot logic implementation, we will basically return this specific index. Now if you observe here, right, anyway 1 is in its perfect position. So what if we divide the array into two parts based on this pivot index as part of the quick sorting algorithm? Now what we will do, from index 0 till index 2, I will call the same, quick sorting, whatever the function that I will implement. From index 4 till index 6, I will call the same recursive quick sorting function that I will implement. In each and every step, the same pivoting logic will be employed. As a result, in the end, we will basically get the entire array sorted. Okay, anyway, I'll explain the quick sorting algorithm once again, but I'm just trying to mention how we will basically divide the array into two parts. Okay, how we will divide the array into left part and right part, just like we divided the array in the case of merge sorting algorithm. So that is the step-by-step process that we follow for finding the pivot index in the array, using which the entire array can be divided into two parts. Now that we have understood the step-by-step process for finding the pivot index in an array of values that we are getting, let's just try to write the pseudocode for the same thing, and let's just make sure that we are writing this implementation in such a way that we can simply reuse this as part of the quick sorting algorithm as well. So here, as part of the pivot index implementation, we will simply write one function called pivot, and this function will basically take an array of values along with the start index and end index in the array. Then we need to search in the range. Basically, as we implement the quick sorting algorithm, right, this function will basically get called, and as part of the quick sorting algorithm, we will divide the array into two parts, right? Basically, in the division, we will make sure that we are passing the start index and end index. Only in that range only we need to operate, because quick sorting is also one of the in-place sorting algorithm only. That basically means that in the whatever the input array that we get, in the same array, in the end we will get the sorted array as well. That's the reason why we will make sure that whatever the start index and end index that we are getting, in that range only we will perform our pivot logic. That's the purpose of this start index and end index. Okay, if you remember the pivot logic that I mentioned, what I mentioned, I will basically pick up the very first value we have in the array, and in the range of indexes that we have got, we basically need to start the logic from the start index till end index, right? Out of all these values, the first value is nothing but whatever the value we have at this start index. So I will define couple of variables called pivot index. This pivot index is nothing but whatever the start index that we are getting itself in the beginning, and the pivot value is nothing but whatever the value we have at that particular index. So we need to move this value to its perfect position, but whatever the value that we are picking, whatever the index that it is available at, it itself could be the perfect position, right? That's the reason why pivot index I am starting with start, and the value is nothing but whatever the value we have at this start index. Okay, now what we need to do, we need to compare this value with the remaining elements that we have in the array. So we have already picked up the start element, so the array of values that we need to compare are available from start index plus 1 till end. Okay, for that I'm simply going to write one loop. It will basically start at start index plus 1 and will basically execute till the end index. In each and every step, what we were doing, whatever the pivot value we have got, this pivot value is basically getting compared with the value at this ith index. Now to compare and swap, I will basically do, if at all, if the pivot value whatever I have got, if this pivot value is greater than whatever the value we have at this ith index, if you remember our step-by-step process, we were incrementing the pivot index by 1 and then we were swapping. So what I will do is, inside this I will simply increment the pivot index by 1. After this I will simply swap the elements at array of pivot index comma array of ith position. Okay, once we are done with this loop, right, we are still not done, because if you remember, we still have not moved 1 to index 3. What we had to do, once we are done with all the element comparisons, in the end we had to swap the element that we had after whatever the index that we have, pivot index, with the index where we picked up the element. That's the reason why once we get here, we will simply swap whatever the pivot index that we have after running this loop and whatever the value we have at the start index. This start index is nothing but the pivot value index that we picked up in the beginning. So we will swap these two. Once we are done with swapping these two values, in the end basically we moved this pivot value to its perfect position such that all the left side values are smaller and all the right side values are greater. And one thing that we have to do as part of this pivot functionality implementation is, in the end we need to return the pivot index. Using that, quick sorting basically divides the array into two parts. From this pivot index, all the left parts will be one part of the array and all the right values will be another part of the array, such that we can recursively call the quick sorting algorithm to again find the pivot in the left part of the array and on the right part of the array, such that in each and every step we will move a particular value to its perfect position, such that in the end we will basically get the sorted array. That's the reason why here I will simply return the pivot index in the end. Okay, so that is the pseudocode for implementing the pivot logic on an array of values that we are getting in the range basically from start index to end index. Okay, once again I'm mentioning, as part of the quick sorting algorithm, quick sorting is one of the in-place sorting algorithm only. That basically means that in the same array, input array that we get, in the same array we will basically get the entire sorted array. To achieve that, as part of the divide and conquer, once we move a particular value to its pivot index, right, we don't need to compare all the values once again for some other value to go to its perfect position, basically to find the next pivot index. So we will basically pass the start and end index such that we will only restrict our logic into that specific block. Okay, so that is the purpose of this start index and end index. Okay, anyway, that is the pseudocode for pivot logic. Now that we have understood this, let's just try to analyze the time complexity and space complexity involved in this, pivot logic implementation. Obviously, when will the best case for this pivot logic will occur? Whenever both start index and end index, whatever the range that we are searching, that range is nothing but having only one value. When we have only one value, obviously whatever the value that we have remained, that itself is a perfect position, right? So ultimately, whatever the for loop that we are running will not even run once, because we are running this from start place 1 to till end. As a result, this for loop will not even get executed, and whatever the assignments that we are doing for pivot index and pivot value, they will get executed, but they are basically going to take constant amount of time. As a result, in the best case scenario, the time complexity will be only order of 1, which basically occurs the range of the array of values that we are searching has only one value in it. Okay, so that is the best case scenario. Obviously, in the worst case scenario, basically we will get an array containing n values. In the beginning, we assume whatever the start index, right? If we are trying to perform this pivot on an array containing n values, basically in the beginning the start index will be 0 and end index will be the last element index, which is nothing but n minus 1. So whatever the pivot logic that we have here, we are running from start place 1. That basically means it runs from index 1 till n minus 1. That means this for loop whatever we have, it runs for n minus 1 number of times, and all these variable declarations and swapping anyway will take constant amount of time only. So the overall time complexity in the case of implementing the pivot where we have array of n values and the range that we are getting is from 0th index till the very last index that we have in the array. In that case, obviously the worst case scenario will occur and the time complexity will be order of basically n minus 1. This we will simplify it as order of n only. Okay, so that is the worst case time complexity. To talk about the space complexity, if you look at this implementation, right, we are only defining two variables. One is this pivot index and the other is this pivot value. After that, again, one more variable for loop is getting declared, but combining all these variables memory, basically if we combine all that, it is going to be constant, whether it is going to be best case or going to be worst case. We need these three compulsory values to be defined. As a result, in the best case, the space complexity is order of 1 only, and in the worst case also the space complexity is order of 1 only. Okay, so that is the entire information that you should be knowing for implementing the pivot logic, which we will reuse it as part of the quick sorting algorithm. Okay, now that we have understood this, let's just go ahead and let's just try to understand how exactly the quick sorting algorithm will actually work.